We're in Chapter 4, Probability. Section 4.1 is Statistical and Critical Thinking. The first definition that we have is probability, and the probability of an event refers to the likelihood that the event will occur. The probability of event A is represented as P of A and is a value between 0 and 1. Outcomes are different ways that an event can occur. Sample space of a probability experiment is a collection of all possible outcomes. An event is any collection of outcomes from a probability experiment, and a simple event is an outcome or an event that cannot be further broken down into simpler components. The first example that we have says a probability experiment consists of sampling M&M colors. Part A says identify the outcomes of the experiment, and the outcomes that we have would be the different colors. And so we have red, I'll go ahead and abbreviate that just as an R, B for blue, yellow, so Y, we have orange M&Ms, we have brown, so I'll put a BR, and we have green. And since this is all their different outcomes, we're going to go ahead and represent this by putting some braces around this. Part B says determine the sample space. The sample space would be actually counting these, and we're going to call that N is equal to, and if you count up all those colors, we have a total of 6 different colors that we could have for our M&Ms. Part C says define the event not selecting blue, red, or green. So I'm going to call this event E, and this would be selecting if it's not red, blue, or green. That would be yellow, orange, or brown. I'm again going to put my braces around this. The next part that we have on here is notation for probability. Capital P denotes a probability, capital A, B, and C denote a specific event, and P of A denotes the probability of event A occurring. Next thing we have is what's called a probability model, and this is going to follow into the next section and chapter that we have. A probability model is the possible outcomes of a probability experiment and each outcomes probability. So a couple things that you have to have. First one is going to be that the probabilities have to be between 0 and 1. And then if you were to add up all the probabilities of all those different outcomes, they would add up to 1. We have 3 approaches for finding probability results in values between 0 and 1. The first one that we have is a relative frequency approximation of a probability. We're going to conduct or observe a procedure and count the number of times event A occurs. And so to calculate the probability of A, we're going to take the number of times A occurred and divide by the number of trials of an experiment. The second kind of approach we have for probability is going to be our classical approach, and this requires equally likely outcomes. If a procedure has n different simple events that are equally likely, and if event A occurs in s different ways, then the probability of A is going to be the number of ways A occurs divided by the number of different simple events that we would have, or s over n. And then the third one we have, which is not as large of a use for us in this class, is called subjective probabilities. P of A is the probability of event A is estimated by using just knowledge of a relevant circumstance. So you're going to have to just use your own judgment. This is difficult for me to grade, and that's why it's not really useful to be used in a class. We have the law of large numbers is a procedure that if we repeat it again and again and again, the relative frequency probability of an event tends to approach the actual probability. The first example that we have on page 2, we're going to go ahead and circle, and we'll discuss this together in class. The next thing that we have is called a complement of an event. This is going to be let A denote an event, then A bar is going to be the complement of event A, is the outcomes in which event A does not occur. The first example says, in a recent year, there were about 3 million skydiving jumps, and 21 of them resulted in death. Find the probability of the complement of the event not dying while making a skydiving jump. So we're going to go ahead and put down probability of not dying And to calculate this, our denominator is going to be the total number of jumps that we have, which is going to be our 3 million. And then to figure out our numerator, that's going to be the number of people that did not die. And to get that value, we're going to take our 3 million and subtract 21, the number of people that did die, and we will get 2,999,979 people that did not die. And that's going to go ahead and be our numerator. Dividing this out, you get 0.99999 and then a 3. So it looks like the probability of not dying while doing a skydiving jump is pretty close to 1. The next thing that we have is the probability of a complement event. And you'll notice that that is going to be the probability of the complement is 1 minus the probability of that event. So the example says the probability of owning a 4-bedroom house is 0.183. What is the probability of not owning a 4-bedroom house? And so probability of not owning is going to be 1 minus 0.183. And this is going to be 0.817. So if under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less than or significantly greater than what we would typically expect with that assumption, we conclude that the assumption is probably not correct. The next definition that we have is significantly high, which we've seen already. And this is going to be a significantly high number of successes. This is when we have the probability of X or more. And the next one is significantly low number of successes. So this would be with a probability of X or fewer. And both of these, if we remember from before, anything that's going to be significantly high or significantly low when we talk about probabilities or the likelihood of an event is going to be less than or equal to 0.05. So for both of those. Next thing we have is called actual odds against event A occurring are the ratio of the complement and the probability of the event, usually expressed in the form of a ratio, A to B, where A and B are integers, and you're going to reduce your ratio. And then we have the actual odds in favor. Event A occurring are the ratio of the probability of A over the probability of the complement, which is the reciprocal of the actual odds against that event. And then we have what's called the payoff odds against event A occurring is the ratio of the net profit if you win to the amount bet, which is equal to the net profit ratio to the amount bet. The next example we're going to go ahead and circle. We'll look at that one together. These odds are good to know when you guys turn 21 and you got to go to Vegas. So next section we have is section 4.2, the addition rule and the multiplication rule. This section discusses the probability that event A or event B occur, or the probability that event A and event B occur. So we're going to be exploring those connective words of or and. In the previous section, we only considered simple events, but in this section, we consider compound events. And a compound event is any event combining two or more simple events. So the next thing that we have is some Venn diagrams, which we typically see in like an English or maybe a social science class. And if you notice in the first Venn diagram, the shaded part in there is where both A and B are occurring. And so our wording is going to be, this is an example of A and event B. And in the second diagram, we actually have all of that Venn diagram shaded for all of A and all of B. And this is our definition of the word or. So usually when I discuss this, we talk about food. And so we would say the probability of us wanting, or if I say I would like a hamburger and a hot dog, that means that I would like both of those. But if I were to ask I want a hamburger or a hot dog, that typically means in English one or the other. But in probability and mathematics, it's actually going to mean one or the other or both. And that's that second Venn diagram that we have here. The next example that we have says a paint store has 9 different colors. We have yellow, blue, red, green, orange, pink, white, tan, and lavender. Let event 1 be selecting blue, red, white, and pink, and let event 2 be selecting blue, yellow, white, green, and tan. Draw a Venn diagram for this example of this paint colors. So I'm going to go ahead and make 2 circles because we have 2 events. I'm going to have them overlapping, and the reason why I'm going to have them overlapping, if you notice in event 1 and event 2, they both have blue, and then they also both have white. So I'm going to go ahead and call the first circle event number 1, and the second circle event number 2. And since blue and white occur in both of these events, I'm going to go ahead and put a B and a W in the middle. And then event 1 also has red and pink. So I'm going to put an R and a P inside circle 1, but not in the part where both of those events are occurring. Likewise, event 2 also has a yellow, a green, and tan. So yellow, green, and tan. And if you look at the colors that were given to us, we actually have a couple that were not included. You'll notice lavender is one and orange is the other. So what we do is we take our Venn diagram and we're going to box it. This is our universe, and our universe consists of everything that we have total. And so that would be all the colors that we have in this example. And so I'm going to go ahead and put down L for lavender and an O for orange. And those are outside of my circles because those are outside of those events. However, they're still colors that the paint store carries. So we have some questions next to that. The first one says, find the probability of event 1 occurring. So probability of event number 1 is going to be, and if you look at event number 1, which is that left circle, there's a total of 4 different colors out of a total of 9 colors that paint store is selling. The next one says find the probability of event number 2 occurring. And likewise, we're going to do the same thing. If you look at event 2, there's 5 different colors. You can look at your Venn diagram or up there in the word problem. And there's 5 out of a total of 9. Both of these fractions we cannot simplify, but if you can, definitely go ahead and simplify. Part C says find the probability of event 1 or event 2 occurring. So we're going to have the probability of event number 1 or event number 2 occurring. And so that would be all of this stuff if you look at the shading up above for the Venn diagrams. So counting those up, we have a total of 7 things inside event 1 and event 2 circles, divided by 9 total. There's a couple of bullet points right below that. One of them says notice that the probability of event 1 plus the probability of event 2, adding these two together, is not equal to part C, which is the probability of event 1 or event 2. And the reason why is because we have blue and white that occur in both event 1 and 2. And if you did this by adding these two together, you're actually counting it twice. It should only be counted once. The next thing that we have is called the addition rule. For any 2 events, A and B, the probability of A or B is going to be equal to the probability of A plus the probability of B. And then go ahead and make this be a minus the probability of A and B. Definitely a formula that we need to know. In Chapter 4, we do have formulas we should have memorized for our exam. The next example says a guidance counselor at a middle school collected the following information regarding the employment status of a married couple within his school boundaries. And so what he's collected is going to be who is working, so either the husband only, the wife only, or both spouses, and the number of children under the age of 18. So it's either 0, 1, or 2 and more. I also want you to notice that we do have some columns and a row there for total. So the first part here, part A, says what is the probability, and just to remember that probability is always going to have an answer between 0 and 1, that only the husband works or only the wife works. So we're going to have probability of only husband works, so I'll put down only H, or, which is our connective, only the wife works. So looking at our table here, only the husband works. We have a total of 425. And only the husband works is going to be the 425, and only the wife works is going to be 126. Total is going to be the total number of people that we have. So since 1700 is our total, that will go into the denominator. And then only husband works is going to be 425, and only the wife works is 126. From here, we're going to add together those two numbers that we have in the numerator and then divide by 1700, and we get 0.3241. The next part says, what is the probability that for a married couple selected at random, the couple has no children or only the husband works? So I'm going to go ahead and erase our circles that we had before. And I want you guys to realize that we still have a total of 1,700 people. So that would still be our denominator. But this time we're going to be looking at the probability that they have 0 kids, or, which again is our connective, only our husband works. So denominator is still that 1,700 because that's our total sample size. And this time we have a lot of different ways to look at this. So I'm going to go ahead and just circle different things that we have. So only the husband works, we get by 425, or you can add up that whole row. Likewise, 0 kids, you get 788, or you can add up that whole column. So 0 kids, we got 788 by adding up 172, 94, and 522. And that gave us a total of 788. Plus, just like the last one, if you look at the husband works, if you were to add up the 425 that we have over here on the right, we'd have an issue because we actually counted that 172 people in there that have 0 kids and only the husband works. We actually counted them twice. So that's not going to work to do this time. So what we're going to do is we're going to actually take this and add in 79 and add up 174. You can also do this problem by using the formula that's listed right up above. There's a bunch of different ways to do this and still arrive at the correct answer. Adding up your numerator all together, getting a total there, and then dividing by 1,700, we get 0.6124. And again, with probabilities, it's very typical to be rounding 4 decimal places. The next page, it says contingency tables or two-way tables relates the categories of data, row variables, and column variables, and we saw that in the previous example. The next definition we have is called disjoint events, or also mutually exclusive events, are two events A and B that have no outcomes in common. So if you look at your Venn diagram, there's no overlapping of those circles of those two events that we have. I also want you to notice that the probability of event A and event B is going to be equal to 0 because there's nothing there that they share in common. The next example says a store has 6 different equally likely colors of paint. This time we have yellow, blue, red, green, orange, and pink. Let event 1 be selecting green or orange paint, and let event 2 be selecting pink paint. So this time, if you notice, we don't have anything in common between our two events. So when I draw my Venn diagram, I'm actually going to draw 2 circles that have no overlap. I'm going to go ahead and call the first one number 1 for event 1 and number 2 for event 2. And event 1 was selecting green and orange. So green or orange. And then event 2 is selecting pink. Again, I'm going to go ahead and put a box around this to symbolize our universe that we're dealing with. And the colors that we did not use this time are going to be yellow, blue, and red. And again, those go anywhere outside of those circles but inside the box. So part B says find the probability of event 1 occurring. So probability of event 1 is going to be, we have a total of 2 colors out of a total of 6. And this is going to simplify to 1/3. Again, you can write this as a decimal. So again, rounding at 4 decimal places, we'd have 0.3333. Part C says find the probability of event 1 or event 2 occurring. So probability of event 1 or event 2 occurring. And so this time we're going to go ahead and count up what we have in event 1 and event 2. And so we have green, orange, or pink. So there's 3 out of a total of 6, which does simplify to 1/2 or 0.5. Next we have complementary events and the addition rule. So the probability of A or A complement from our formula before is going to be the probability of A plus the probability of A complement minus the probability of A and A complement. However, this we saw earlier, since they are complements and they would have nothing in common with one another, would just be equal to 0. So this would just simplify to being the probability of A plus the probability of A complement. Conditional probabilities denoted P of F given E. So this is read the probability of F given E. It is the probability that event F occurs given that event E has occurred. So the next example is going to look at that new word that we have that we're going to see in our probability problems. So the first example says suppose a single die is rolled. What is the probability that the die is going to come up with 3? So the die, you can either have it land 1, 2, 3, 4, 5, or 6. So the probability that we're going to roll 3 is going to come up with just 1 out of our total, which is 6. So 1/6. Part B, though, is different. Part B says we are now told that the outcome is going to be an odd number. So we are given information and hence a conditional probability. So we're now told that the outcome will be an odd number. What is the probability that the die is going to come up with a 3? So this time we know. So what's the probability that it's going to roll a 3? Given, and we use that straight up and down line that we saw up above, given it's an odd number. So now that we know that it's an odd number, it takes our sample, which is going to be 1, 2, 3, 4, 5, and 6, but we know that it's odd. So right now I know it's not a 2, it's not a 4, and it's not a 6. So what happened? Our sample just got smaller, and so instead of it being out of 6 different numbers, I now know that it would be out of 3 different numbers. And if you look at those 3 that we did not cross off, there's only 1 that is a 3 that we would like. So it'd be 1 out of 3. It says notice down here that the conditional probability reduces the size of the sample. So the next thing that we have is called the conditional probability rule. Definitely one of those formulas we need to know. It says if A and B are any 2 events, then the probability of B given A is equal to the probability of A and B divided by the probability of A. Or if we're counting items, it's going to be the number of times that A and a B occur divided by the total times that number A occurs. The probability of B occurring given the occurrence of event A is found by dividing the probability of A and B by the probability of A, or dividing the number of outcomes in event A and B by the number of outcomes in A. The next example that we have says the following data represents the number of speeding tickets issued to individuals in the past year and the gender of the individual. Determine the following probabilities based upon the results of the survey. So you'll notice we have females, males, and 0 speeding tickets, 1, 2, or 3 that were issued in the past 12 months. We also have a total column and a total row. Part A says, what is the probability that a randomly selected individual was issued a ticket last year given the individual is female? So we have the probability that they were issued 0 tickets given that they are a female. So in order to do this, we don't have to deal with probabilities. I'm going to go ahead and count these since we do have a table. And this is going to be using the formula that's listed right up above here. It's going to be the number of people that have 0 tickets and are female divided by the number of people that are female. So from here, total number of people that are female is going to be 115, and that's going to go ahead and go in our denominator. And then the numerator is going to be the number of people that have 0 tickets and are female. And so 0 tickets and are female is going to be that 97 in here. Dividing this out, rounding 4 decimal places, we get 0.8435. The next part that we have here, part B, says what is the probability that a randomly selected individual is female given that the individual has not been issued a ticket in the past year. So this time for this problem, we're actually asking for the information backwards from what it was in part A. So we're going to ask for the probability that the person is going to be female given that they had 0 tickets issued in the past 12 months. So looking at our table up above, we're going to use our number, and our formula is going to be the number of people that are female and have 0 tickets divided by the number of people that have 0 tickets. I want you guys to realize that it's always divided by what is given, which in this problem is A. So from here, the number of people that have 0 tickets in this problem is going to be 168, and that's going to go in our denominator. And then we have the number of people that are female and have 0 tickets, which is going to be 97. Dividing this out, we get 0.5774. Part C, we're going to go ahead and circle, and we will look at that one together. You can go ahead and try it on your own and see if you can get the correct answer by yourself. The next example that we have says, according to the U.S. National Center for Health Statistics, 0.15% of deaths in the U.S. are 25 to 34-year-olds whose cause of death is cancer. In addition, 1.71% of those who die are 25 to 34 years old. What is the probability that a randomly selected death is a result of cancer if the individual is known to have been 25 to 34 years old? So the issue with the word given is that it's not always used, but there's equivalent words that are used in English that represent given, and known is one. So if you know something, it cuts down your sample space. So for this, we want to know the probability that the selected death is going to be a result of cancer, given, or that it's known, that the person was between 25 and 34 years old. So using our formula, this time I'm not going to be using number because we actually have probabilities. Those probabilities are not written as decimals, they're written as percents, but that's easy to change. And so in order to, I'm going to use the formula from up above. So we're going to have the probability that we have a person passed away from cancer and they're 25 to 34 years old. So cancer and 25 to 34 years old, divided by the probability that they're 25 to 34 years old. So the probability that they're 25 to 34 years old and they've passed away is going to be that 1.71%. And we need to write that as a decimal, so move your decimal to the left twice. We're going to get 0.0171. And then in the numerator, we have the probability that they passed away from cancer and they're 25 to 34 years old, which if you look up here, it does say 0.15% of deaths in the U.S. are 25 to 34 years old whose cause of death is cancer. And so that would be our probability. Again, moving that decimal place twice to the left. Dividing this out, we get 0.0877. And again, rounding 4 decimal places. The next definition that we have is using the multiplication rule. We have a formula here. This is the probability that 2 events A and B both occur. So we have the probability of A and B is going to be the probability of A times the probability of B given A. If we have independent and dependent events, it's going to make our problems a lot different. So independent events is going to be the probability that one event occurs in no way affects the probability of the other event occurring. They're independent of one another. And dependent means that one has an effect on the other event. So the probability of one event occurring influences the likelihood of the other event. So the next example that we have says determine whether events E and F are independent or dependent, and then justify your answer. So we'll briefly discuss that. So the first one we have is event E is speeding on the freeway, and event F is being pulled over by the police officer. So this is an example of dependent events. And the reason why we would say these are dependent is probably you got pulled over by the police officer because you were speeding on the freeway. Part B says event E, you get a high score on the statistics exam, and event F is going to be the Dodgers win a baseball game. And unfortunately, these have nothing to do with one another. These would be independent events. And just because you do really well on your statistics exam, it does not influence our baseball game for the Dodgers or any other team. Next thing that we have is called the multiplication rule for independent events. And so this is only if A and B are independent, then the probability of A and B is going to be the probability of A times the probability of B. And we have an example here. This is according to the National Vital Statistics Report, 20.1% of all pregnancies result in a weight gain in excess of 40 pounds for singleton births. In addition, 49.5% of all pregnancies result in the birth of a baby girl. Assuming gender and weight gain are independent, what is the probability that a random selected pregnancy results in a girl and a weight gain in excess of 40 pounds. And we're looking for a probability. And so we're going to have the probability that it's a girl and we have a weight gain greater than 40 pounds. And so if you look at this, it does give us a really big word in here. It does tell us that they are independent of one another. Sometimes you have to read the problem and look for those words, and other times you kind of have to understand the problem in order to get that it's implied in the problem. And so we're going to take the probability of having a girl times the probability of a weight gain greater than 40 pounds. And so the probability of having a girl is going to be the 49.5%, but again we need to write this as a decimal. So we have 0.495 times the weight gain of more than 40 pounds is going to be 0.201. Multiplying these out, we get an answer of 0.0995. Next thing that we have is sampling with replacement and sampling without replacement. So sampling with replacement is going to be the selections are independent events. And so sampling with replacement means you would select an item like a marble or a card, and then you would look at it and then put it back. And then sampling without replacement would be where you keep that marble or you keep that card. And those are going to be dependent events because taking that one has an effect on selecting the next item. So when sampling without replacement and the sample size is no more than 5% of the size of the population, we can treat the selections as being independent even though they are actually dependent. So the next example we have says assume that 3 adults are randomly selected without replacement from 247,436,830 adults in the United States. Also assume that 10% of adults in the United States use drugs. Find the probability that the 3 selected adults all use drugs. So the probability that all 3 use drugs. And now it does say without replacement, and without replacement does say that they are dependent. However, right below that, it does say that if your sample size is no more than 5% of the size of the population, then we can treat the selections as being independent even though they're actually dependent. So since we're only dealing with 3 people, that's really small compared to the 247 million adults that we are talking about. So I'm going to go ahead and treat these as being independent. So treat as independent. And so we're going to have the probability that the first uses drugs times the probability that the second uses drugs times the probability that the third uses drugs. And we saw that up above for independent sampling. And again, it would be the probability that all 3 uses drugs. So probably the first does, and the second, and the third would be our connective word. And the probability that the first person uses drugs is 10% or 0.10 times the probability the second would be the same, and times the probability the third would be the same also. Multiplying this together, we get 0.001.